Welcome everyone to the 2023 BioPhotonics Conference. Thank you all so much for joining us, and in this session you will hear from Julien Charton, who co-founded Alpao and currently serves as Chief Scientific Officer. Julien works to develop adaptive optics with improved wavefront correctors for emerging applications, and today he will show us how to select wavefront correctors for adaptive optics in microscopy. If you have any questions or comments, you can type them right into the conference chat box that is on your screen, and if you missed part of today's session, you can always come back later and watch it on demand. Julien, we appreciate you taking the time to present at the 2023 BioPhotonics Conference.
Okay, so thank you, Jacob, for the introduction, and thank you also for all the organization. So my talk is, as you said, about adaptive optics, and I will try to focus on biophotonics application, because as you may know, adaptive optics is now used in many other applications, such as astronomy, defense, or optical communication. So the outline of this talk is very simple. I will just say a few words about the Alpao company, what we are doing. Then I will go to the quick overview of adaptive optics, how it works, what are the principles, and what are the control methods. Then I will show you a few examples of real adaptive optics systems, so you can have a feeling of what it looks like, and a few applications, again, focused on biology. And then, because it's very new and very hot topic now, it's a small introduction about new control methods that can be used for adaptive optics using machine learning algorithm. So just a few words about Alpao. So we were founded in 2008 in France, and we are designing and producing a lot of different products for adaptive optics, including wavefront corrector, wavefront sensors, and software and full systems. Of course, we are a very international company because adaptive optics is a worldwide market, and we typically produce more than 700 deformable mirrors up to now, and we are a bit more than 40 people in the company. So the big question is, why do we need adaptive optics? In this very simple sketch, what you see, I will change my pointer so you can see it. So imagine you have an object, a cell, for example, an optical system. In this example, it's a microscope objective with some optical lens. And what you want to do is an image. And what you want, of course, is a sharp image of the object. So this is what you want. But in the real life, most of the time, what you have is a blurred image, or not as sharp as you want, in particular in biology. And the problem is that most of the time you have some perturbation in the sample itself, or maybe in the optical system that is not perfect, and most of the time in between the object you want to see and the optical system. So this perturbation can be anything that will locally change the index of refraction of the medium. And the effect is that after the microscope objective, for example, instead of having a very flat wavefront, you will have some bumps on your optical wavefront. And as you see in this diagram, the result is that all the light coming from this bump will not focus where it should be on the camera sensor in this example. And this is why what will make your image completely blurred. So the problem is the wavefront that is not flat, and we have to find a way to correct for this. So this is where adaptive optics come into the game. So you still have your optical setup, your perturbation, and the answer is very simple. You put a wavefront corrector that will restore the flatness of the wavefront, and this is really what is important to get a sharp image. Of course, it can be a CCD camera, it can be not an image, but an optical fiber where you want to put all the light to do some spectrography, for example, or any other kind of optical sensors. So adaptive optics really is the goal of adaptive optics is to correct for the wavefront. So how can it work in practice? Most of the time, the Wavefront corrector is what we call a deformable mirror. There are other techniques, but I will focus on this one because it's easy to understand. The idea is that you just put a regular mirror, but behind the mirror, you have small actuators that can push and pull on the surface and make a bump onto the mirror that will compensate for the bump onto the wavefront. And this is what will give you a flat wavefront and give you the sharpness of the image. So I will not go into the detail of how deformable mirror works, but just to quickly show you what we are using at Alpao. There are similar technologies using other actuators and other control methods. What we're using at Alpao is a very thin reflective membrane. You see it in red in this image. And below the membrane, we have a number, so it can be hundreds up to thousands of little actuators. We are using electromagnetic actuators, so you have little coils, little magnets, and this is what will allow you to push and pull the membrane and to correct for the wavefront. So like for any optical component, what is important when you have to select a deformable mirror is, of course, the diameter, the coating, but also the number of actuators that will be like pixels on a camera. The more you have pixels, the more accurate you can work, but there is a cost, of course, and also the speed at which you can change the correction. So now the question is, you have a wavefront corrector, a deformable mirror, but how do you control? How do you know what kind of actuator command you have to send to correct for the wavefront? There are different methods. I will start with the most simple way. So again, this is a very simple schematic of an adaptive optic system with you have your wavefront, you have your perturbation, you have your deformable mirror, and you just have your camera, the camera where you want your image to be sharp. And what you can do is just use a simple metric. So it's a simple processing that you are doing on the image. For example, a contrast measurement or a brightness measurement on some region of your image. And you are using the software, computer, to try many different shapes on the deformable mirror and to try to select the one that will make the best image. So this is the good point, is that you are using really the metric, that is the most interesting for your application. It can be the contrast, it can be the flux injected into an optical fiber. So you are really optimizing what is important. The drawback, of course, is that it can be quite slow because you have to make many iterations. There are different optimization algorithms, but at the end, it will always takes you like hundreds of iterations before you can reach a sharp measurement. And just a comparison, it's a bit like autofocus in a simple camera or smartphone. This is the same principle. You are trying different focusing on of your objective, and you select the best one, the one where the image is the sharpest. So this is the same principle, except that you don't have only one actuator, you have many of them. So it's a bit more computing intensive. So this is the first method, efficient but slow. The other way is that you add some specific hardware to your setup. In this example, so you still have the deformable mirror and the camera, but in between, you put, for example, a beam splitter that will take part of the light, and using this light, you will feed a wavefront sensor. So this is a specific sensor, a sensor that you have to add. It's basically a camera with some special optics, and this will give you a real measurement of the wavefront. So in one shot, you can compute the error on the wavefront and send the command to the deformable mirror. So it's a more direct approach. So it's very faster. It can run at the speed of the wavefront sensor camera, basically. But of course, there is a cost, is that you have a slightly more complex optical setup, and you need one more camera, one more optical sensor. like for the deformable mirror, I won't go into the detail of wavefront sensors, but just to give you an idea of how it works. The most common kind of wavefront sensor that is used in adaptive optics is what we call a Shack-Hartmann sensor, from the name of the inventors. So it's a camera. Any camera can be used. Of course, you may need an infrared camera or a very sensitive camera or a very fast camera, depending on your application. But the key is that in front of the pixel array, you put a set of micro lenses that will completely change the image. So you see the principle on the right. Here you have the small micro lenses, you have the pixel array, and this is the image that you read on your computer. So if the wavefront is flat, this is a perfect position, then every lens will focus the light on a little spot, and the image will be a grid of little spots, very well aligned, very accurate grid. If the wavefront is not flat, each lens will produce a spot that is a bit shifted, and the image will still be a set of spots, but they will move. And actually, the position of each spot will give you the wavefront, or to be more accurate, the gradient, the local slope of the wavefront. And this is what can be used by the computer to compute the correction to be done. So this is a basic principle. Now I will give you a few examples of real adaptive optics systems. The first one is very simple. This is what we call a demo kit, or an evaluation kit. So this is a small breadboard. You see it. It's typically 20 centimeter is the size, where you have all the required components to practice adaptive optics and to really do useful correction. It can be also used for training or purpose. So what you have is an optical source. It's a simple LED with a fiber. Then you have a deformable mirror that we produce, and you have a small wavefront sensor. So this one, of course, is not using a very expensive camera. It is using a simple CMOS camera. And of course, you have a few lenses and optics, relay lenses to focus the beam where it should be, and adapt the size of the beam on each component. So you see that an adaptive optics system can be quite simple. And the idea of this kit is that you can start with something that is rocking out of the box. You also have a software. You can use some scripts. You can use MATLAB. You can use Python. You can use any software you want. And of course, you can use a graphical user interface if you prefer. And when you are ready, you can, if you want, dismount the components and install each component into your own optical setup, or maybe select more different components for example, infrared camera, or a more faster deformable mirror, for example. So this is more a demo system. To see a more systems that are really used in the real life, you have two examples for biology here. You have a system that we developed for microscopy. So as you may know, in microscopy, you have the main microscope from Leica, Zeiss, Nikon, and you have some ports on each side, and then you put your camera or spectrometer or whatever instrument you need, or laser source, on the side of the microscope. So you have a lot of modules that can be plugged onto your microscope. So this is why in this kind of application, probably the good way is to have all the AO system in a box that you put in between the microscope and the sensor. In this case, I think it's a spectrometer or an OCT system. So this is one example in a microscopy. Another example, which is quite different, is in retinal imaging, so vision science. This system has been developed by the Duke University, and you see that it's a very, very compact and portable retinal camera that can be held in front of the patient. And this is very important for small kids or people that have that cannot sit in front of a standard retinal camera. So in this case, Alpao provided the very compact deformable mirror that is here, and the Duke University did all the optical system and software. Now let's go for a few applications. So again, in microscopy, you've seen the setup. So now what are the results, typical results? So if you look into a tissue, so not only a cell, a few cells, but a real tissue, when you try to go deep into the tissue with your microscope, of course, the light will go through a lot of structures that will act as perturbation onto the optical beam. And the result is that even if you have a perfect microscope, the image will not have the quality that you expect. In particular, if you go deeper and deeper in this example, it's like 200 micron, because after this you have a lot of scattering problems that is a different story. So this is what you have, and with adaptive optics, you can really recover the sharpness of the image. So this image was produced by the Eric Betzig team, and he won the Nobel Prize for all this work about adaptive optics and microscopy. Another result in ophthalmology and retinal imaging. So just quickly, if you go to the doctor and you want to have an exam about your eyes, one of the main one is to look at your retina and try to see if there is any problem on it. So this is the retina, this is the eye, this is typically what this kind of instrument looks like. The problem is that what you want to do is actually microscopy into the eye. And even for people that are having a very, very good eyes, it has not the optical quality of a microscope. And what you see is really nothing if you try to zoom onto the photoreceptors cells inside the eye. So this is a real image, and with adaptive optics, you can really completely change the game and look at the rods and cones onto the retina. And this image is also a good way to answer one question that we commonly have about adaptive optics. The question is, why don't you use just a computer algorithm to recover the sharpness of the image? Using AI or other computer software, now you can do fantastic things. And the answer to this question is on this slide, actually. This is the image that you have without adaptive optics. There is no way that you can improve it because there is no image, there is nothing to see. So you first have to improve the signal with some hardware. So this is the role of adaptive optics, to get this kind of image. And after this, you have some signal, you have something to improve, and you can use AI or other algorithm to process or improve even better this image. But the first step is to have some signal, and for this, you really need some hardware. You really need to correct for the wavefront. So this is for the classical adaptive optics, hardware and control. I will very shortly introduce some new methods that a lot of people are working on it around the world in many application fields. And the key is to use new machine learning techniques to control adaptive optics, so to have better correction of the wavefront. So if there are some experts about machine learning, please apologize me, because I'm not an expert, and this is just a very, very short and quick introduction. So I will take many shortcuts, and it's really focused on adaptive optics. This is not supposed to be a global overview of machine learning, of course, in a few minutes. So for those who are really new to this field, just a short explanation. So you see again the same simple layout of an adaptive optics system, and as we explained, the question is, okay, you have some signal, camera pixel from the camera, for example, and how do you compute really the command, so the signals that you will send to each actuator of the wavefront corrector? This is a problem. So we've seen that there are some classical algorithm. So it's a direct solution. It means that actually somebody, an expert, has to make some mathematical model of the problem and to write the equations, and then somebody has to translate these equations into a computer program. So with a lot of classical programming techniques. So if there is this feature, then you have to do this on the wavefront corrector. So you have to an expert to write these lines. And in adaptive optics, most of the time, the output, so the output is a command to the deformable mirror, is equal to the input from the wavefront sensor multiplied by some matrix. This is a linear problem, and this is why most people are doing. So this is the classical algorithm, the direct solution. So it is not machine learning. Another way to do it is what we call the stochastic algorithm or Monte Carlo approach. And again, this is, you don't really know the answer to the problem, but you try many solutions and you try to converge to the best solution. So the new way to answer this problem and to guess what is the command you have to send to the deformable mirror or wavefront corrector is using machine learning. And the approach is very different. And the idea is that you still have a program, but it will somehow mimic what the expert would do after some training. So there is no explicit programming of what is the formula, what is the equation, but there is a training phase. So what is this training, and what is actually how can machine learning may be implemented? A very recent and successful machine learning techniques, because there are many of them, is what we call neural networks or deep learning. So the idea is that instead of having a very long list of instructions for the program to compute the command for the wavefront corrector, your program is divided in many single processing units that are very similar to neurons in the brain. And the key, so you see in the picture, every green circle is a neuron. So of course you have to code this into your computer, but it's just the same small piece of code repeated a large number of times. They are all connected, so it means that the input of one simple processing unit will be the output of the layer that is before. So you have this kind of layer approach. And when you say deep learning, it just means that you have a number of layers. So of course, you have to put some measurement at the input layer because there is no other layer before. And of course, you need to use the output. And in our case, the output will be considered as a solution to your problem. And the key is that you have to estimate the quality of the solution. So you have the learning or training phase that is very important. So the idea is that you take many inputs, you see what is output, you estimate the quality of this output for your problem, and then you will tune the gain. And there are many algorithms to do this, but the basic idea is that if one of the gain, so one of the link between neurons, contributed in a positive manner to a good solution, you will increase a bit the gain. And if one link contributed to a poor solution, you will reduce the gain. So after many can be millions or billions of iterations, the magic about this kind of neural networks is that when you present a new input at the input layer, it will produce an output that makes sense, that is what you expect. So this is a basic principle. Now the question is, how do you transfer this to adaptive optics in a real case? Well, again, we have our simple AO system, so with a flat wavefront, a perturbation, and a wavefront corrector and a sensor. And the key is that in this example, you may use directly the pixel values of your image or part of your image, and you will use it as the input of your first layer of neurons. So you see that in this example, you only have 4 neurons. In real life, you may have the number of neurons equivalent to the number of pixels in your image. So this is the key, that it can grow to a huge number of neurons, and this is why we have great progress recently, just because the size, the power of the computers are large enough to handle larger number of neurons and get some interesting results. So the input is the pixel values of your image, and the output is again a set of scalar numbers, a vector of numbers, and you, for example, can use this vector directly as the position of each actuator. So for the training phase, what you do is that you get many different images of blurred objects. Most of the time, at the beginning, the output is just useless, garbage. But after some time, it will start to produce a good correction, so a sharp image of the objects that you are testing. So you do this a number of times. So it takes time, but when it's done, so you have set all the little gains on your neural network. If you present a new image, and actually this is what you want to do, not an image that you know already, a new object, a new sample, a new microscopy image, then it will, in one shot, so this phase is very short, can be just milliseconds, produce a vector of value that will produce a very good shape on the deformable mirror and produce a very sharp image. So this was just an overview, but it's very important because well, there are a lot of research in this area, and the good point is that it is long to train this kind of neural network, but after this, it's more robust. Even if the image is not exactly as well, like what you expect, it will give you a good correction, and you don't need additional hardware you don't need a wavefront sensor, you don't need a complex optical layout. The complexity is more in the software and not in the hardware. So of course, for industrial products, this is very important, because even if you take some time to train the neural network, after this, the recurrent cost of your instrument or device will be lower, because the value is mainly in the software part. So I hope this was a good introduction for those who did not know adaptive optics. This is the end of the talk, and of course, questions are welcome.
Thank you so much, Julien, for sharing your experience and knowledge of adaptive optics for microscopy. Just to repeat your message to everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 3rd annual BioPhotonics Conference. Thank you all so much for joining us.
Thank you.